Here I am back to talk about gears. During a previous presentation I modeled the two wheels of a Spur Gear. I had tried to use the parametric capabilities of the Fusion 360 software. So, for example, it was possible to change the number of teeth of each gear wheel, or the pressure angle, or the module, or any other parameter, and then let the program remodel the gear. At the end of that previous presentation I had changed the number of teeth of one of the wheels into a small number. This wheel could then be called a pinion. It turns out that pinions usually need to undergo a tooth profile shift in order to mesh properly. This profile shift requires an adjustment of the center distance between the pinion and the ring with which it is to be meshed. The difficulty lies in the calculation of the center distance because it does not depend only on the pinion that has undergone the profile shift, it depends on the pinion ring pair constituting the gearing as a whole. One of the parameters that must be calculated to determine the center distance is the operating pressure angle. For any gear without profile shift, this angle is the same as the standard pressure angle. As soon as a tooth profile shift is needed on a pinion or gear wheel, the operating pressure angle differs from the standard pressure angle. Unfortunately, the operating pressure angle cannot be solved analytically. However, there is an excellent analytical approximation. Alpha being the operating pressure angle, we have to find the inverse of the involute function, tangent alpha minus alpha. Mathematicians Taylor and Maclaurin propose a method to exprim any function in a polynomial series. In general, it is enough to consider the first terms of the series to obtain a good approximation. The first three terms of the series of the involute function are null. By choosing to keep the fourth term only, the involute function is simply written as a single polynomial term of the third degree. Determining the inverse involute is now easy. However, Maclaurin imposes that his series be accurate only in the vicinity of 0. For our needs we work with angles varying from 14 to 35 degrees, which corresponds to values ranging from 0.24 to 0.61 radian. I propose corrections to reduce the inaccuracy due to this deviation from 0. A linear regression correction gives an error of less than 1% for alpha between 15 and 32 degrees. With quadratic regression the result is better with an error of less than 0.1% for alpha between 16 and 36 degrees. The best approximation is obtained using rational polynomials. The precision is impressive with 6 or more significant digits up to alpha values of 37 degrees. Even for angles up to 45 degrees a precision of 4 significant digits is obtained. One could not hope for better. The coefficients proposed in this animation are valid for alpha expressed in radian. Our Spur Gear is finalized. It is fully parametric with the possibility to adjust the center distance between the two wheels. I use it as a basis to model a helical gear. I keep its parameters whose values are adjusted to take into account the helix angle. They are updated from a CSV file. I delete the features of the Spur Gear in the timeline to keep only the sketches. I start by modifying the sketch of the pinion. I will complete the profile of the half tooth to obtain a complete tooth. When modeling the Spur Gear I used the mirror feature after extruding the tooth half. This operation is now performed in the sketch because a helical gear tooth is not symmetrical and therefore cannot be extruded by halves. I thus duplicate the tooth profile flank by selecting the radius of the base circle, the points that sample the circle involute, and the arc of the tip circle for the mirror feature. The mirror line is the radius of the tip circle. I end the sketch by drawing a spline running through each point of the symmetrical involute, making sure that it is tangent to the symmetrical radius of the base circle. I am now creating a second sketch for the pinion. It contains a point obtained by projecting the pinion center point from the first sketch. Then from this point I draw an axis whose length corresponds to the pinion thickness. That's it, this second sketch is complete. It's the turn of the sketches of the gear wheel. I proceed in a similar way to the pinion. I keep silent to allow you to better concentrate on the elegant and strange ballet of lines and curves displayed on the screen. I'll be right back, just after the second sketch of the gear wheel. Here we are with a modified sketch and an additional sketch for each gear wheel. I now proceed to the modeling of the pinion. I generate a cylinder by extruding the root circle. I continue by extruding a tooth using the sweep feature. This is where the axis drawn in the second sketch comes into play. The two extrusions are joined into a single solid body. I continue with a fillet at the root of each tooth flank. I complete the modeling of the pinion by applying a circular pattern of the last two features, the tooth sweep and the fillet at its root. The circular pattern is applied as many times as given by the number of teeth. Unsurprisingly, the modeling of the gear wheel is similar to that of the pinion. One extrusion, one sweep, one fillet, and one circular pattern. The helical gear has some advantages over the spur gear. It has improved tooth resistance due to the longer support of its helically wound base, thus offering greater strength and increased load capacity. The axial tooth overlap also allows more teeth to mesh simultaneously, resulting in smoother and quieter operation. The free choice of the helix angle also allows, curiously enough, a certain flexibility in adjusting the center distance. The tooth profile of a helical gear can be perceived perpendicular to its axis or perpendicular to the path of the helix. In the later case it is said to work in the normal system. The parameter cos beta allows to switch from the standard system to the normal system by choosing 1 or cosine beta as value respectively. Helical gears are generally calculated according to the normal system. I change the helix angle as well as the gear thickness to conclude this presentation. This is where all the pleasure of working with a parametric software lies, changing parameters.
Now the final word. Happy New Year!